This is for tensile strength. Tensile strength is indicated by the maximum distress rate curve, and it generally says where necking will occur. This property is very dependent on the preparation of the specimen. So if you're running a film, say it's half a mil or a mil thick, and you try to cut it and you have wrinkles on the edges, game's off. You have to have a perfectly square sample with no fringe on it whatsoever. Sometimes it takes longer to make your samples than it does to do the testing. Another thing to remember for tensile strength, there should be no breaking in the grips. If you start having breaking in the grips, you got to try a different grip. Whether you go to a rubber faced or you go to a smaller grip, whatever, you don't want a sample to break in the grip. Your numbers are all void if that happens. Here's another one where it's detecting the right there. This would be the maximum point. The sample probably didn't break until right about there. It's probably necking here, and then right about here it probably broke. But this is considered your maximum point. So what you do here is to get it in stress, you take your pounds and divide it by your cross-sectional area and your width of your sample. You get your size. Yeah. Or whitening of the plastic. Here's our environmental chamber with the, this we can do at temperature also. We can get up down to about 30 below and up to about 200 degrees. I think the extensometers will take 220 before they're done for. Yeah. Yes. That little extensometer, this little piece right here, that little piece right there is an extensometer. For us, we don't have a video extensometer, and you couldn't use a video extensometer inside of a box anyway. So this little extensometer measures the distance this thing is moving. What happens is there's compliance in the grips. There's compliance in all these joints. Even the load frame has a certain amount of compliance. If you don't use an extensometer, your modulus numbers are going to be off. So you need to use an extensometer. That will also give you the modulus or the stiffness of that sample. Here's what you were talking about. Yield strength is the lowest stress that gives you permanent deformation of material. In some materials like alumina alloys, the point of yielding is hard to define, thus they usually give you as a given required at 0.2% plastic strain. And this is 0.2% yield stress. Here's some examples. This one is a zero slope yield. The sample is, here's your modulus. It comes up, and all of a sudden it plateaus off. Where this first starts, the difference right on that point is where your zero slope yield is. And that is you can give that number as the material is necking more than likely. And then after it necks, the load actually goes down on this particular one. Some of them they go down, some of them they go down for a period of time, and then they'll go right back up again and break. Depends on the material. Here's your offset yield. This is moving at 0.2% yield strength, and they go up to this line. You can see that this isn't quite flat here. It's still going up just a little bit. So they're trying to give you an offset yield, and that would be your offset yield. Here's your elongation, and it's where you meet the x-axis right here. So where this curve meets the x-axis, that's your percent elongation. And that is the end of it. Any questions?
You ever integrate that curve to get a measure of toughness?
We have. It's not as accurate as you'd like it to be on quite a few materials. We've done it for polyethylenes and things of that nature with relative range numbers. There's a machine, that device you can buy to actually do that for an instrument. You probably get better numbers on. Okay, that's what I got there.